We're going to continue with Big Idea 6 today, and we've already introduced quite a bit of this. We talked about reversible reactions that are in dynamic competition. They're in equilibrium. We talked about how perturbations such as temperature, pressure, volume, as well as, what's the other one? Concentration, affect equilibrium. We talked about the fact that temperature is the only factor that affects the value of KEQ. And hopefully you feel very comfortable with Le Chatelier's principle. What we're going to talk about today is an approach called RICE, and I'll go through all the pieces with you. I think you'll be very successful with it, but it does require a lot of practice. What's going to happen here is you're maybe provided with initial conditions. You may be provided with a Kc value and asked to find amounts of substances or pressures at equilibrium. You may be given information about equilibrium and asked to find information initially. And we're going to set up this RICE approach today that's going to be used throughout this 9 weeks, because you're going to use it with equilibrium reactions, and you're going to use it with acid-base equilibria, as well as solubility equilibria. So we're going to talk a little bit about illustrative equilibrium calculations. One note here, I'll get back to this. It says if volumes of gases and reactants and products are the same, you don't have to include volume in your calculation. Leave in moles rather than molarity if they're asking for moles in the answer. What that means in English, and this actually came in to play on your mini quiz, but you got lucky because I gave you a volume of 1 liter. So in that case, moles and molarity were the same, but a lot of you put moles in your Q expression where it really needed to be molarity because the delta N of the gas wasn't 0. What I mean in regard to the delta N of the gas being 0, for example, if you had 2 hydrogen iodide in the gaseous state in an equilibrium reaction with hydrogen gas and iodine gas, remember the delta N of the gas is equal to the moles of gaseous product minus the moles of gaseous reactant. So in this case, you have 1 plus 1 is 2, and you have 2. 2 minus 2 is, of course, 0. And if delta N of the gas is 0, you can do KEQ or Q expressions with moles instead of molarity, because the volume piece would just cancel throughout because it would be the same. And this will come into play in a little bit, and I'll show you where you can do it. But if the delta N of the gas is 0, that's when your KEQ expressions, instead of doing molarity, can be done in moles. It's just a time saver, and I'll get back to that. What we're going to be doing is setting up the RICE approach. The first thing we're going to do is try and calculate Kc or Kp from experimental data. Previously, when you were calculating Kc or Kp, equilibrium concentrations or equilibrium pressures were provided to you, so it was very easy. You know, for example, from this reaction here, that the Kc expression would be concentration of products over concentration of reactants. A capital K there, you're talking about equilibrium concentrations. However, sometimes you're not given equilibrium concentrations. You're given initial concentrations, and you need to figure out how to get equilibrium concentrations. If you weren't given Kc, you'd probably be given all the initials and 1 equilibrium, and that will allow you to find the other equilibrium concentrations. And this approach is going to be our Rice approach. R for reaction, I for the initial concentration. This can be in molarity or moles. It can only be in moles if the delta N of the gas is 0. C for change, whatever the unit for the I you'll continue with, and then E for the equilibrium concentrations, and you make what's called a Rice or an ICE table. And that's what I'm going to show you here. The first one is penned out for you, at least in regard to the framework. I'm going to rewrite it, and this way we can work through all of it. It says begin with 1 mole each of phosphorus trichloride and chlorine gas in a 1 liter flask. Begin with, initially you have, starting with, these amounts are initially placed in a container. That tells you you've got initial amounts. Also, looking at this reaction here, is the delta N of the gas 0? No, it would be -1, 1 minus 2. So you have to use molarity, not moles. Based on the fact the volume is 1 liter, it's relatively straightforward. It says when equilibrium is established at 250 degrees Celsius in this reaction, the amount of phosphorus pentachloride present is 0.82 moles. When equilibrium is established, so in red we have equilibrium conditions. Calculate Kc, reminding you concentration expressed as molarity is moles of solute over the total volume in liters of solution. So here's my framework. Let me show you how to fill in the pieces. I'm going to transfer over here, and what you're going to make is called a Rice table. R for reaction, I for initial, C for change, E for equilibrium. Here's our reaction. I'm really going to try and spread this out because you're going to be writing in this table, and it's a little bit easier if it's all spread out. And these are all gases. I was told initially we had 1 mole each of the reactants, and because the volume is 1 liter, we actually have concentrations of reactants of 1 molar. They didn't say anything about how much product we have, so we're going to assume that it's 0. And if you don't have any product, in which direction must the reaction go in initially? Forward, because you don't have any product. Moles of the phosphorus pentachloride is 0.82 moles divided by 1 liter is 0.82 molar. E for equilibrium is equal to the initial amount plus the change. If the reaction is going in the forward direction, what must happen to concentrations of reactants? They will decrease. You will subtract from each of these either a specified amount, or if you don't know what the amount is, you do in this case, but I'm going to walk you through it backward, you're going to subtract x. And in this case, it's 1x because the coefficient of each reactant is 1. If the coefficient here were 2, we would be subtracting 2x. If the coefficient here was 3, we would be subtracting what? 3x. Now this gets generated. So we're going to add some quantity, in this case we'll call it x, and again coefficient of 1, so it's 1x. If the coefficient were 4, it would be 4x. Now in this particular instance, we can actually figure out what x is. Using this piece right here, if 0 plus x is equal to 0.82 molar, then x has to be 0.82 molar. If you had 2x here, then you would divide it by 2 to solve for x. So you actually do know that x is 0.82 molar. That's my change. And I don't know if this is a little tricky the way I wrote it. X is equal to that, so you are subtracting. So what's 1 minus, or 1.00 molar minus 0.82 molar? And these are the equilibrium concentrations of the reactants now. Now you have the equilibrium pieces, so you can in fact solve for Kc, because that's what they're asking for. So Kc is equal to, if they asked for the expression, you would write it. They didn't ask for the expression here, but very often they do, and sometimes the kids don't know what to write. Now it becomes a plug and chug situation. And I wrote 0.18 molar out twice. I probably would have just squared it. It's easier, but just in case it wasn't clear. And you've got a Kc value of 25. Is the setup here clear? Okay. Now, I also just want to point something out. This just becomes a little math type trick. Let's say, for argument's sake, that this was 0.50 molar and each of these were 0.10 molar. You have to be able to do this without a calculator in some cases. This one not so much, but right here, yes. Whatever approach you want to take is fine. I tend to go into scientific notation. And solve it this way. I know 5 over 1 is 5. This is that, and then -1 minus -2 is +1, so my answer is 50. So again, without the calculator, you have to be able to work through it. You're going to see a lot of these types of questions in the multiple choice section. I highly recommend when you do your practice quiz on those multiple choice questions, no calculator. It sounds mean, but it's the best thing for you to prepare well for May. All right, so this is how you work through it when you have initials and you have a piece of the equilibrium and you're solving for Kc. This Rice approach will be very helpful. In the next problem, we're going to work through it from scratch, and there are a few caveats in here I want you to see.
So the temperature does nothing?
The temperature must remain constant, otherwise the value of Kc could change. So what they're telling you throughout there is that the temperature is 250 degrees Celsius and it doesn't change. Now in this particular reaction, they didn't specify whether it were endo or exothermic. You could actually figure that out at this point because you could get the delta H's of all of those. This happens to be a synthesis reaction. Most synthesis reactions are what? Do it this way. Most decomposition reactions are endo because it takes energy to bust things up. Most synthesis reactions, not all, are exo. Okay? So if it's exothermic, you would put the energy term here. If I decreased the temperature, equilibrium would shift in the forward direction to replace the heat lost. If equilibrium shifted in the forward direction, the value of Kc, because of the temperature change, would increase. Because if you shift in the forward direction, what happens to the amount of product? It will increase. And if you look right here, if you increase product concentration, you can see the direct effect on Kc, or Q, depending on how you word it. If you're making an alteration, you would do the Q piece. All right? Some of you have some concepts a little bit jumbled there. Be careful. I hope you did some equilibrium practice. Some of you learned about it last year and you don't think you need any practice. I think you do. All right. In the next example, we've got a kilogram of antimony 3-sulfide and 10 grams of hydrogen gas, and they're going to react in a 25-liter container at 713 Kelvin. At equilibrium, 72.6 grams of hydrogen sulfide gas is present. We want to know the value of Kc under these conditions, same temperature, and the reactions given. There's a lot going on here. Sometimes you see these problems and it becomes completely overwhelming and you don't know where to start. If we're talking about equilibrium, is anything about a solid relevant in a Kc expression? No, so I don't really care about the solid. Nice to meet you and goodbye. All right, we know that the mass of hydrogen gas initially is 10 grams. We know the volume of the container is 25 liters. We know the temperature is 713 Kelvin. At equilibrium, we know that the mass of hydrogen sulfide gas at equilibrium is 72.6 grams. We want to know the value of Kc. I also want to make sure that you truly understand what you have to do when. I gave you information initially and at equilibrium. that tells you need a Rice table. Now in some textbooks they'll call it ICE tables because they don't include the R for reaction. It's all the same. The reaction's in there. Rice it out. Here is your equilibrium reaction that is given. And again, that's a solid, not included in an equilibrium constant expression. Hydrogen gas, equilibrium reaction. What's the delta N of the gas? 0. So I could do this in moles. Because if I have volume to the third power over the same volume to the third power, it just goes away. So why bother doing it? It's not worth it. I need to convert this to moles. This you learned in honors. 1 mole of anything is equal to its mass in grams. And just be careful where you put things now. This is my initial, and this is my finishing. That's my initial setup. Doesn't say anything about initially having any hydrogen sulfide gas, so I know the direction must be going in which direction? Forward direction. Hang on one sec. Questions here. Here's your setup. One last piece. If you're going forward, what will you subtract from here? Not x, but 3x. And what will you add here? Can you figure out what x is? And x here is 0.713. Now in this particular instant, it's pretty easy because you already know what 3x is, but I want to make sure you can solve for x. That's an important point. But in this case, the 3x, if you will, we know is this. So 4.96 minus 2.14 is 2.82 moles. And now I want you to solve for Kc. Write the expression and solve for it. Did you get what I got? Yes? Alright, so now you know how to set up rice tables. And now we can do it with a couple of different applications. And that's what you're going to see in the next few problems. Now we're going to be calculating quantities, typically equilibrium amounts from Kc and Kp values. So you might be given some initial amount, and you might be given the Kc or Kp, and now you can set up the table such that you can solve for the missing pieces. For example, it says start with initial reactants and no products. If you don't have any products, in which direction must equilibrium shift? Forward, so that you make some. And you'll also be given the value of Kc or Kp. You can do these tables with concentration, or you can do them with pressure. It doesn't matter. As we said already, you're going to use X to identify one of the changes in concentration or pressure that occurs in establishing equilibrium. If the coefficient's 1, you'll use 1x. If the coefficient's 2, you'll use 2x. If the coefficient's 3, you'll use 3x. You just have to figure out if you're going forward or reverse. If you have no products, you have to be going forward. You subtract from the left side, you add to the right side. For example, generation of hydrogen iodide gas from hydrogen and iodine, Kc value of 54.3 at 698 Kelvin. It says begin with. Are these initial amounts or equilibrium? Initial. So it'll say begin with, start with. You initially place. Those are all initial amounts. Look for any type of wording, and this is where the homework problems will really help you. Begin with 0.5 moles of hydrogen gas and 0.5 moles of iodine in a 5.25 liter vessel at 698 Kelvin. You want to know how many moles of each gas will be present at equilibrium. So in your setup here, be very cognizant of what they are providing to you. They're telling you that the moles of hydrogen gas initially is 0.5. They're telling you that the moles of iodine vapor initially, 0.5. That's because I'm writing on the ceiling. Sorry. Thank you. They're telling you you have a volume of 5.25 liters. They're telling you the temperature is 698 Kelvin. They want to know how many moles of each gas at equilibrium. So that's what's given, and now what we need to do is we need to figure out how to set it up. And I realize this is in your notes already, but let's go ahead and set the table up from scratch, because sometimes it's important to see the derivation. Here's our rice table. We've talked about how to generate these. We've got hydrogen gas, iodine vapor, and 2 moles of hydrogen iodide. We know initially that we have 0.5 moles. Why can I do this problem in moles? The delta N of the gas is 0. In addition, they're asking for moles at the end, so why bother dealing with the volume? So initially we have this. How do I know the reaction's going in the forward direction? Because you don't have any product. Also, they gave me Kc in the problem. I didn't write it initially. I'm throwing it in right there now. So I know initially I have none of this. And that's all the information that we've been given. I know the reaction's going forward. Why am I going to subtract X from each reactant? Because the coefficients are 1. I know the reaction's going forward, so I've got to consume it. How many x am I going to add here?
2.
Where'd I get the 2 from?
Oh, good.
All right. So now I've got 0.5 minus x, 0.5 minus x, and 2x. My Kc expression, if asked for, hydrogen iodide squared over hydrogen gas over iodine, Kc is equal to 54.3. And I'm just going to go ahead and square these because this times this would be squared. How do I solve for that? Can I take the square root of both sides? Sure I can, because this is squared, so the square root of it would just be that. So I'm going to take the square root of everything. So the square root, now without a calculator you'd get a nice number like 49, but the square root of 49 is what? 7. And the square root of 64 is?
8.
So this is somewhere between 7 and 8, probably closer to 7, right? So the square root of that is 7.37. That's equal to 2x over this. And then you can just solve it. Now I'm going to cheat with my calculator because my calculator has a solver function which anyone with a graphing calculator has. You may not know how to use it. I'll show it to you. This would be solvable relatively easily, and usually they're not this tough. In any event, if you wanted to solve this, my calculator is a little different. We can put up a TI-84. If you have the Inspired, that one, you usually know how to use that better than I. But what I've got here is I'm going to go to my solver function. My function's easy to find. Yours on the TI-84 is in the math piece, but there's a lot of different ways you can get to it, and I can walk you through that. I've got 7.37 times 0.5 minus x, close, minus 2x. I'm going to hit enter. I'm going to set that equal to 0. I'm going to move down to the x, and I'm going to hit my solve button, and poof, out pops the answer, which is x is equal to 0.393. Now some of the calculators are a little bit different, and I'll walk you through how to use yours, or you can go ahead and solve it. It's not terribly difficult. It's not like you need the quadratic. But this is my x. So how would I figure out how many moles of each gas I have? What would I do? Yeah, just plug it in. So you have 0.5 minus 0.393, that's 0.107 moles for both of these. And what about the hydrogen iodide? What do I do to the x? Multiply it by 2.
So how do you do it on the calculator?
You have an 84? Let me try and do yours under the screen. Who's got the Inspire? Did you figure that one out? All right, so you'll show us that. Do you know how to do the 84? Or you? All right, let me see. There's a couple different ways to do this one. I think we were hitting the solve button, so green enter, maybe. No. Let's go to math and fly down to numeric solver. I'm going to put that expression in, 7.37 times 0.5 minus x, close parentheses, minus 2x. I'm going to go here, I'm going to put a 0 in because that's what I have to set it equal to.
Shouldn't it be divided by 2?
No. It's this times this minus this is equal to 0. I can do it. It's, see, this times this minus that equals 0. Do you see it?
Yeah.
Okay. And then I think you just hit alpha solve. And there's your answer.
What's a solve? Enter?
Yeah, it's a green enter. It says solve above it. See, it doesn't show that nice on the screen. You want me to do it again?
Yeah.
Okay, let's try it again. I've never played with this calculator, so sometimes I don't really know how to clear it. So we did math. We went down to numeric solver. I put this in here. I went down and put a 0 in. I'm going to clear that, and I just hit alpha enter for solve, and poof, it's there. Fun, fun, fun. All right? If you have a different calculator and you don't know how to use it, I'll take a look at it. Mine's really old, but mine's like the easiest one to solve off of, and I always get the right answer. Because sometimes if you've got quadratics, you can get 2 different answers. Mine always gives the right one. Some of the other ones were giving different ones. So don't worry about it. They're not going to ask you to solve a quadratic. I'm going to show it to you because it's interesting, but it's not something you're going to see. However, this is a question that you can often see. It says, how do the equilibrium quantities compare? Now we went ahead and solved it, but let's make some inferences here. What can you say about moles of hydrogen and moles of iodine? They are the same because their coefficients are the same. But what if the coefficient of this were 2? How would these equilibrium amounts compare? You'd have more of this than you would of this because you would have taken more away, correct? In a ratio? All right. So be careful there when you look at different types of responses. And we'll get into that type of questioning in your practice quiz. But that's sometimes what they ask you. Not for the actual values, but for a comparison. All right, let's see if you can do this one. I can set it up with you if you want, or if you think you're ready, you can rock it out now. It says, consider the following reaction. The Kc is given. Temperature constant. You have 0.1 moles of each reactant in a 5-liter flask. You want to know how many moles of hydrogen gas will be present at equilibrium. And then I want to know the partial pressure of it. You want to set it up together or you want to try it yourself? Okay, so I'll just do it on paper and then we'll compare. You want the question on the screen? Here you go.
Oh, it's
wash your hands in the sink.
It's in the back.
Oh, I think it's almost empty. Just wash your hands in the sink. There's paper towels. So the problem set up, you can see in regard to the rice table, what you started with. You know you have to go forward. You subtract 1x from each of these because of the coefficient. You're adding to this side. You set up your KC expression, substituting. KC is given at 23.2. Go ahead and solve it. And again, you can throw this right into the solver button. In this particular instance, you didn't even need to set it up to solve for X. So I know at equilibrium, hydrogen gas, 0.0828 moles. If you didn't recognize that you could do the whole table in moles and you did it in molarity, that's perfectly fine. What will pop out is your equilibrium concentration of hydrogen gas, and then you would go back and multiply it by the volume, which is 5 liters. Once you have this, then you can go ahead and solve for the partial pressure of hydrogen gas at equilibrium, because you know PV equals nRT. Now let me ask you this. Let's say I ask for the total pressure at equilibrium. How would I solve for that? You could get the partial pressures of all of them and add them up. That's one way. And if you had a table where you had pressure, definitely go ahead. If you had all the equilibrium pressures, you could add them up. But what might be a little bit easier here?
Could you add up all the moles?
Yeah,
Plug that in?
I think that's what I would have done, absolutely. And so if you were asked for total pressure, you would have the total moles at equilibrium as such. So you could get the moles across the board, add them all up, and plug that in there to get the total pressure. And these are all questions they ask because they go back and link you back to gas laws. And you'll see on the part 2 of your AP exam, you're also going to start to see it now. These types of questions link into gas laws very much. You can also link it back to thermodynamics, because if you have a Kc value, you will know if the forward or reverse reaction is favored. You'll know delta G. Looking at the reaction, you can't really say much about the entropy here, because you go from 2 moles of gaseous reactant to 2 moles of gaseous product. But if the delta H were given, you could drive it in that regard. So there's a lot of ways to link it back to many concepts that you have mastered thus far.
When you get X, what do you do with it?
Well, what did you get as your X?
I got that.
You got that?
I went back and did
Okay, so once you get the X, that will be the equilibrium moles of the products, and you just do 0.1 minus this to get the equilibrium moles of these, if that were asked.
But it was asking for each.
Right, so you just popped right out, because in this case, H at equilibrium is equal to X. Is that the Inspire?
Yeah.
Mahi? Help. I don't know how to use that one. And I'll go play with Mr. Marr today, and hopefully he'll teach me.
So you click menu and then click
Anybody else have an Inspire? You know how to use it?
and then
Okay.
plug in whatever.
That's like a YouTube videos.
One extra step.
Yeah, some of them are really tricky to use. All right. There's one more piece to the puzzle. I'm going to show it to you. It's with the quadratic.
Comma and then X, since your variable is X, and then we'll enter it.
There's commas.
There's one more place. There's one more piece, and that does involve quadratics. They'll never ask you to solve something with the quadratic. So some of the examples for the rest are far too advanced, and I didn't give you any of these in your homework. I pulled them all away. but there are a few concepts in the remaining examples that I do want to show you. And then I pulled a problem from an old AP exam that I thought was absolutely delicious. And so I thought that would be a really big help to you. All right, so let me show you this. This is where the solver button with the quadratic is a godsend. But we'll go ahead and walk through. If the initial amounts of reactant are not equal, then you're going to need the quadratic because you're not going to be able to take the square root of both sides. You know that quadratic can be, you can solve for something using the quadratic where x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. You've seen that since Algebra 1 many moons ago. Now clearly nobody wants to do this anymore, and you throw it in your solver function and out pops the answer. So we can take a look at that. But I want to just show you a few pieces of the puzzle here. And this is something you might do in college chem. It says consider the following reaction. Again, you're generating hydrogen iodide from hydrogen gas and iodine vapor. Kc is given. You're not beginning with the same amount of starting material, and that's a hint the quadratic would be needed, but they won't give you one like this on the AP exam because they think it's unfair if people have fancy schmancy calculators and other kids don't. So they won't give you one like this. That's the initial amount the Kc is given. I just want to review a few points. How do you know the forward reaction is favored? Don't have any product. How do you know you're subtracting 1x from the reactants?
There's no product, you're going in the
No
forward
product,
reaction.
you're going forward, and their coefficients are 1. You are correct. How do you know you'll add 2x and not x to the right side? Coefficient of 2. So you've got this mess right here. You can take the square root. You'd have no choice but to throw it in the solver function or quadratic it out.
Would we ever get one that goes in the reverse direction?
Yes, and we're getting there. So you could go ahead and solve it. And again, too extensive, but I just wanted to mention it exists. And toward the end, if you want to practice that solver function, we can take a look at that. Maya's question was excellent because she said, well, would you ever go in reverse? And the answer is yes. Those of you who stepped down for the picture, we mentioned this, and we're going to do it here. It says, if the initial mixture contains all of the reactants and products, that is to say, initially you have reactants and you have products, how do you determine the direction of favorability, forward or backward? You have to calculate Q. You have to calculate Q, and you compare it to K. It can be compared to Kc or Kp. And be careful, because we've done a lot with concentration. I'm going to set one up with pressure with you. You have homework problems on pressure, and you might see it on your quiz. Be careful. For example, forming phosgene from carbon monoxide and chlorine gas, the Kc is given. Initially, you've got all of this in the flask. This is the first time we have thrown in reactants and products. You've got a 10-liter flask, and the temperature is held constant. On the AP exam, it may say, would the forward or reverse reaction be favored, and justify your choice, just like I did to you on the mini quiz. Not to be mean, but you can't move forward if you don't have the beginning pieces mastered. Why did I have to put this as concentration? The delta N of the gas was not 0, so here you had no choice but to use molarity. So I've got to get Q. Now on your mini quiz, some of you were sloppy and you did moles, but you got away with it because the volume was a liter. Be careful there. Here's my Q. And it's greater than the Kc that's given. So if Q is greater than Kc, which reaction is favored? Reverse. So if you're running in reverse, you will subtract from which side? The right side. And that's what you're seeing here. So if you have initial amounts, you have to figure this out. It's usually not as complex as something like this, but you have to figure out if the forward or reverse direction is favored. Why are we subtracting 1x from the products? The reverse reaction is favored, and there's a coefficient of 1. We're adding 1x to the reactant. Solving this would be excessive. They won't ask you to do it. But understanding whether the forward or reverse reaction is favored is fair game. Look at this one. Reaction is given, Kc is given. How many moles of each reactant and product will be present when equilibrium is established? Initially, you contain hydrogen gas and hydrogen iodide only in a 5.25 liter volume. Now, they won't ask you to solve for equilibrium amounts because it's too hard. However, why must the reverse reaction be favored?
Because they give you the product.
And they don't give you any look in yellow at what's given. They don't give you any iodine. So if you don't have any iodine, you don't have any iodine to react with hydrogen gas. So which reaction has to be favored? The reverse. Okay? Why would the amount of reactant at equilibrium be greater than the initial amount of reactant? Because the reverse reaction is favored, so reactants get generated. Those are the types of things they'll ask. These types of problems to rice out are too tough. But do you recognize what's given? Do you recognize which direction equilibrium must shift in and why? That's the key. I also wanted to mention this. You can use changes in partial pressure. So the change piece would be off pressure. Here's your reaction. Here's your Kp. It says that the sample of phosgene is introduced into a constant volume vessel and observed to exert an initial pressure of 0.351 atmospheres. Would the forward or reverse reaction be favored? Reverse, because you don't have any reactant. So which side would you be subtracting from? All right, and in this case, if they give you pressure, your initial pressure here would be this. You don't have anything initially of this, so you zero out. And now, would you add or subtract? You would do what to the left side? Add, because you are going in reverse. Would you add or subtract to this? But to this side you would. And how many x's? Because the coefficient is? All right, and then this one would be too tough to solve. But the setup is important. And what I want to spend the remaining time doing, this is the Part 2 question from the 2008 exam, the A form. You have all of this in Google Classroom, number 1. Now, unfortunately, when I fly this stuff in, it is a little bit blurry. I can pick it up off the original AP exam. But I thought this was an absolutely delicious, fat-free question. And it won't add extra calories to your diet.
Is it edible?
It is a healthy snack. It's not edible. That's just silly. Here we go. Let's talk it out and let's do it. It says solid carbon and carbon dioxide gas at 1160 Kelvin. I wouldn't copy the question. I told you what it is. You can yank it up. We're placed in a rigid 2-liter container. And the reaction represented above occurred. As the reaction proceeded, the total pressure in the container was monitored. When equilibrium was reached, there was some carbon remaining in the container. Results are recorded in the table below. I have one question before we start. If I throw more carbon in that reaction, is there an effect on equilibrium? No, because carbon is a solid. Careful. Alrighty. Now, they gave you a table, the dreaded data table. Well, that's enough to make anyone freak out. Time versus total pressure of gases in the container at 1160 Kelvin. At what time is equilibrium established?
8 hours.
8 hours. Good.
Only if that was the question.
The first question is the easiest. You pray for one of these. Write the expression for the equilibrium constant Kp, so you don't want concentration, for the reaction. Go. Write it. Oh, you already did it? You're not even listening to me carry on?
C squared.
All right.
CO2.
So did you do this? I'm going to go ahead and write the equation up here because I think it'll be easier. So Kp is equal to the pressure of carbon monoxide to what power? Correct? Easy peasy?
Parentheses, right?
Yeah, you don't need brackets because it's not concentration.
If you put brackets, is it fine?
As long as you've got pressure in there. That's important. All right, calculate the number of moles of CO2 initially placed in the container. Well, how in the world are we going to figure that out? And if you don't know what to do, the first thing you're going to do is take a deep breath and figure it out.
What was
Don't
the
panic.
moles of CO2?
It says calculate the number of moles of CO2 initially placed in the container.
Next question.
Nope, you can do it. The key word is initially. So what do you know initially? At time 0, what's the total pressure? The total pressure of the gases is 5 atmospheres, right? And it says that solid carbon and CO2 at 1160 Kelvin were placed in a rigid 2-liter container. All right, so the volume is 2 liters. And the only thing placed in that container initially, in terms of gases to exert pressure, was carbon dioxide. So what do you think? What are we going to do?
PV equals nRT. Sulfur N.
Can you use the total pressure initially? Why can you?
Because CO2 is the only gas in there, so total pressure is partial pressure.
That is correct. So initially, the total pressure has to be equal to the partial pressure of CO2 under initial conditions, because that's the only gas in there. So you've got PV equals nRT, N is equal to PV over RT. So the moles of the gas is going to be the pressure times the volume all over the R Am I too low? I'm always so little. Alright, there we go. And we said the temperature was what? 1160 Kelvin. And I get 0.105 moles. Is that what you got?
Exactly.
All right, and let's keep going now. I want to make sure you have a few more pieces under your belt, and then you can finish up the question if need be. It says, for the reaction mixture at equilibrium, the partial pressure of carbon dioxide is 1.63 atmospheres. So the partial pressure of CO2 at equilibrium is 1.63 atmospheres. I was just writing down that piece. Partial pressure of CO2 at equilibrium is 1.63 atmospheres. First, they want me to calculate the partial pressure of carbon monoxide, and then they want me to calculate the Kp. Looking at that table, what information is helpful?
At equilibrium, the total pressure is 8.37.
So what can we do?
Subtract the partial pressure of carbon dioxide.
So that's the partial pressure of the carbon monoxide, correct? Okay. How do we get Kp then? How do we get the Kp? We already wrote the expression. So the partial pressure of carbon monoxide is this, and we're going to square it. And what's the partial pressure of CO2 at equilibrium?
1.63.
Okay. This we got by subtracting in the previous problem,
Okay.
and this was given.
Is this how every question is like?
These are some of the older questions, and this one is pretty pure on being an equilibrium-based question. What we're seeing more of now is there's more linkage, and at the end I can give you an additional question with it that would link it together. But in terms of the data table provided, here's the answer thing. I didn't want you to see that yet. In terms of the data table provided, that's what you are seeing more of.
That's hard.
It is tricky. Look at this. It says, if a suitable solid catalyst were placed in the reaction vessel, would the final total pressure of the gases at equilibrium be greater than, less than, or equal to the final total pressure of the gases at equilibrium without the catalyst? Hunter. Why?
Because the catalyst only changes the activation energy of the reaction.
Definitely on the right track. So you are absolutely correct in that it is equal, and you are correct in that a catalyst affects reaction rate by providing an alternative pathway with a lower activation energy. But how can you link it more to equilibrium, Ben?
The forward and reverse reaction rates would both increase at the same, or increase the same, so that equilibrium doesn't change.
That is correct. So both the forward and reverse reaction rates would be affected the same, and as a result, there would be no effect on equilibrium.
Do we have a quiz next class?
I don't know. All right.
What?
I'll get to that in a minute.
Did we even get a practice quiz? No way.
Look at this last question.
Yeah.
It says in another experiment involving the same reaction, a rigid 2-liter container initially contains carbon plus carbon monoxide plus carbon dioxide, each at a partial pressure of 2 atmospheres. Is the information about the solid relevant? No. But there's a partial pressure of each gas at 2. Predict whether the partial pressure of carbon dioxide will increase, decrease, or remain the same as the system approaches equilibrium. What would your approach be here? You would have to find Q to see if the forward or reverse reaction is favored. So I'm telling you, you have 2 atmospheres for both. Look at this Kp. The Q would be written the same, except you would have initial amounts. They're both 2. Be careful. What would the Q be? You'd have 2 squared divided by 2, so you'd have 2. So your Q is 2. What's your K? 27 and change. Is Q less than, equal to, or greater than K? Less than. And if Q is less than, the forward reaction would be favored. The question was, predict whether the partial pressure of carbon dioxide will increase, decrease, or remain the same. It would decrease because Q is less than K. The forward reaction is favored, and carbon monoxide would be consumed, thus exerting a smaller pressure on the container at equilibrium. All right? That one I can write out for you. But this is a great little question. In regard to what you want done for next time, and you will not have a quiz next time, you're not ready. Let me rephrase. You will not have an 100-point quiz next time. For next time, I want your practice quiz done. I want your homework problems done. I want you to read the lab that we are going to do. I will post that today. I wrote myself a hey dum dum note to post it, and I'll get that done right now. I want the pre-lab done.
Can I have a practice quiz?
questions? All right, so you're seeing the Rice effect, critically important for success in this unit.